Hi, Bhavesh. Am I audible?
Yes, sir.
Okay, thank you. Mm, yeah, I hope my screen is visible.
Yes, sir.
Okay. Okay, so these are the problems. I think both the problems are similar in the graded and non-graded assignments.
Yes, sir.
Mm, BBP2 with Newman boundary conditions, solving initial value problem, containing four additional initial guesses. Yeah, they are similar. Fine. Diffusion with reaction non-linear. Consider the following ODE boundary value problem. Zoom it a little bit for better visibility. Consider the following with C is equal to 1, C1 0, plus L is equal to 1 as the total length, beta is equal to 20, and K is equal to 0.5. Choose a step in this, and please record the results below. Solve the above ODE. Put the value of C at 0.5. I solution at L is equal to 0.5. Okay. So let us first create the parameters. We have two parameters. Param dot beta is equal to 20, and the parameter is could be 0.5. I will create the functions first. You want me to do it using boundary value BBP solver or the finite difference approach? Yes, I will show using both the approaches.
Sir, with the both.
Okay, okay. So function will name this PC just for clarity, because you can name it anything. And this as C. So the first one would be BC1 is equal to, okay, let us just make that X, Y only, because then DC is a little bit confusing. dy1 comma 1, then dy2 comma 1. So this is y2 is basically dc by dz. So the next term would be, I will input parameters. So parameter beta multiplied by y1 This is my function. Next, I need a function for the boundary conditions, right? So I will create that. BBP boundary function, boundary conditions. Then put z and y. Um, yeah, we don't need the parameters inside this. So that's 1 comma 1 was we need two inputs, right? One for the left boundary, so I will just write that as YL, and one for the right boundary, so YR. Uh, for the left boundary, we have C0 as 1, so that would be YL 1 minus 1. That is our first condition, first boundary condition. The second one would be YR2 minus, sorry, not 2, 1. Because the both the boundary conditions are on the concentration only, they are not on the derivative of it. So then like it's like we'll comment this. So y1 is equal to c and y2 is equal to dc by dz, and this is 0. So we have the function and we have the boundary conditions. I think this should be good enough. Next, we need the mesh, like on what points we need the solution to be. Okay. So, 1D mesh for solution points. So that would be so the L, like the length of the fin or whatever fin is. So we'll just create a linearly spaced array from 0 to 1, 20 partitions. So we need to have a bound, like initial condition function, right? So just name it y init, vvp init. So it takes x, so that is like the values for which the mesh grid values. So that would be like z val for us, and then the initial values that we want. So think okay, they have not given the values, but they have given us the h value, right? So yeah, so I will change this z then, because they have given us the h value. So which is 0.1. So I will make this 0 h and 1. And y init I will just take as what should I take? Just take. First one is the rate of change. The first one is the concentration. So let us take that as 0. And the other one is dc by dz. So let us take that as, because from 0 to 1 dc is decreasing, like it's going from -1. No, it's going from 1 to 0. So let us take some negative dc by dz. So we'll just take -1, and that should be good enough. So now we'll just write the syntax for BVP. OD function z comma y function. parent. Next one is the boundary condition function. So that would be VVP PVP BC. Next we have we need the initial conditions, right? So that is we have already made that by init. Yeah, that should be good enough. Next we will just plot it to see the solution. So zval comma solve y first. Yeah. One. Let me run this. Yeah. So this is the plot we are getting. Starts from 1 and goes to 0. So I hope the solution is correct. Yeah. So we want they want us to report the value of C at 0.5. Okay. So let us take this one. First one is the C values, and these are the X values. So 0.5 is the sixth element. So that is 0.0706. 0706. Is this clear or you have any doubt?
No, sir, clear. It is clear.
Okay. Next, they want us to do work for beta is equal to 2. So I'll just change this to 2 and run this thing. Yeah, rest everything is same. Now at 0.5, it's 0.3938. 0.3938. 0.3938. Yeah. Okay. So let us just check first, like if we are getting the correct answers for these or not. Yeah. So these two are correct. Fine. Now let us do the same thing using finite difference approach. Okay. So before that, let me go back to my tablet so we can write it out like what do we need. Stop sharing.
Okay, sir.
And I will share the system. Where is it taking? Um, right here only. So the problem is d square c by d z square is equal to case beta beta c upon k plus c. So we can discretize it as ci plus 1 minus 2ci plus ci minus 1 upon h square is equal to beta ci on k plus ci. Okay, so this is nonlinear, highly nonlinear. Let's try to do something. ci plus 1 k plus ci minus 2ci k plus ci. So this is ci. I think this is highly nonlinear distance approach. This division term, right? It is making this. I don't think we can convert this into a matrix form to resolve using LTM. Yeah, so Bhavesh, I think we need to use something like solve to do this. We cannot simply convert this into a matrix form to. We cannot
Sir,
convert this into a matrix.
it is given in the second example that we should consider t double derivative as alpha t minus t, something like this. Newman boundary in problem 3, I think.
No, but where is it given?
In third problem.
The ghost point approach. No, see, this is a different problem. This problem, the third handling Newman boundary you are talking about, right?
Yes.
Yeah, so this problem is actually linear. This problem is not non-linear in nature. The
Okay.
issue with this problem is the one that we are seeing right now. So I will just show you the problem, like third problem. That problem is d squared t by tx square is equal to alpha t minus ta, right? So this is a linear problem because here the non-linearity comes from this 1 upon k plus c term. This is making this non-linear. So we have these multiplications, right? Ci plus 1 ci and ci square ci minus 1 ci. So what this will do is like usually what do? We convert this into a matrix in sort of like ax is equal to b, right?
Yes.
So here this A matrix is like all the coefficients of this A matrix are constant. They are not changing. So
Okay.
it's basically a linear problem, right? In this case, what is happening? The problem is becoming non-linear because of these multiplications,
Okay.
these three terms. What we can do is we can use Epsol. So I I need to think how can we formulate this as a PM problem. But we can use Epsol to solve like there we will have for h is equal to 0.1 we will have 11 nonlinear not 11 10 nonlinear 10 nonlinear equations. So we can use Epsol to solve all of them together. Let us see how we can do that. So if I create some program like I will share my screen now. My screen is visible, right?
Yes, sir.
Fine. So we can create something. Uh, function. So h is equal to let us take h as input. It will be h is equal to 0.1. No, not h. Sorry. So h as input. The number of elements would be 1 by h. Let us make dy. So the first term we already know that. Yeah. So let us just write what all we know. So we know that y1 is equal to 1. We know that yn plus 1 is equal to 0. And this is not dy, this is just write it as just try c determine ctd as input c. Now I know that c0 is 1, c1 is 0, So we have n known to us. The other parameter is beta. Let us take that as 20. The other parameter is k. So we take that as 0.5. And then n is number of terms for I is to 1 to n. This is a good name. 6. Mm, so we need to convert that equation into some sort of. So let us combine all the items together. So then we will get minus 2k minus 2 minus beta h square minus ci minus 1 plus ci minus 1 and plus ci plus 1. Ci is equal to, yeah, that should be good enough. So that is an I plus 1. Then this should go from 2 to n. Uh, and I know that cz1 is equal to 1, c0, and cz and plus 1 is equal to c1. Then for c2 we can write this as minus k multiplied by c I minus 1 minus c I plus 1 I plus 1 and divided by. So what I'm doing is basically when we write the FDM equation, we get all I showed you, right? We got all those nonlinear terms. So I just collected all the terms containing ci together and the other terms containing like all the other terms to the other side. So I'm just writing c I in terms of all the other variable, all the other c's, right? So there should be cz,
Okay.
uh, and in the division I would get something like. mm, Just need to make sure that my calculations are correct. Ci plus 1 Ci plus kci plus 1 minus 2 kci minus 2 ci square plus ci minus 1 times k plus ci minus 1 ci is equal to beta h square ci. This is correct. Then I collect all the ci terms. That would be uh, minus 2 minus 2 term. Collect all the squares together. Square minus 2kci square minus 2k plus ci minus 1 Plus 3%. Okay. So that should be MATLAB. I think the vector is roots. Yeah, -3 to the equation is not like second order in terms of CI, so we need to do something about it. I can divide this by CI then, but then both the terms would be dependent on CIZ. That is not good. Solve cannot solve that. What should I do?
Okay, sir. Don't worry about it.
Yeah.
Can you please explain the linear form of that differential equation in problem 3 using backward difference formula? That option 1 is written in problem 3. So can you please explain that the
This one,
last
problem 3, which part or option 2?
no non-graded non-graded
No,
assignment
non-graded, but
as
okay,
week
fine.
10 assignment 10, the same assignment. Problem 3 in that problem the linear form of equation is given.
Fine. So the problem is double prime is equal to alpha t minus t a. At the left boundary, t0 is equal to 100, and the last problem is 0. Then alpha is equal to 4, t is equal to 25, and c is equal to 0.1, which is fine. We don't require that. Okay, I think we require that. Yeah. You want me to solve option 1 or option 2? I will do both. So for first, we consider backward difference formula for the last location. If we do that, the last of the tridiagonal equation will be of the form this. Please report the value of a n. And so for the node n plus 1, if we write the equation, then that would be p n plus 1 minus uh, pn. Consider backward difference formula for the last location n plus 1. If we do that, the last row of the tridiagonal Newman boundary condition. Okay. Yeah, so we know the boundary condition for that. So that is h is equal to what is the value? 0. So that means Tn plus 1 is equal to Tn. I think this should be good enough. So what they mentioned is that since it's a Newman boundary condition, we have been given this derivative at the last node. So if this is n plus 1, this is nth node. So we have been given that the rate of change of temperature, not rate of change, like Tt by dz, z is 0 at this point. So we write this Tt by dz at this n plus 1 node using backward difference formula. So that would give us this value. That would give us Tn plus 1 minus Tn divided by h. That is basically dt by dz at n plus 1th node. And we know that this is given to us as 0. So this will go that side, and we just get Tn plus 1 minus Tn is equal to 0. So based on that, value of an should be, so they want us to write in terms of Tn plus n plus 1 Tn plus 1 is equal to b. So this n plus 1 becomes 1, n is minus 1, and b is equal to 0. Just enter that. An minus 1, n plus 1, 1, and b as 0. Let's check my scores. Yeah, so those three values are correct. So this is clear, right, Bhavesh? Next, we will do the ghost point approach. So ghost point approach, in this approach, we write the finite difference formula for the domain at the last node. This will result in finite difference equation in Tn plus 1 and Tn 2. The additional point n plus 1 is called ghost point. To eliminate ghost point, we write the Newman boundary condition using central difference formula at n plus 1. This will result in another equation having involving Tn plus 2. Okay. Yeah, Bhavesh, you left the meeting. This first problem, is this clear to you?
Sorry, sir.
Option.
There is an internet problem.
Yeah, sure. What they want us to do in option 1 is they want us to write the backward difference formula for this Newman boundary condition. So that will give us something like this: Tt by dz is equal to Tn plus 1 minus Ts upon h. And we know that it is given to us as 0. Okay. So that is the equation, just that. So we take this h to that side, and we get this equation: Tn plus 1 minus Tn is equal to 0. And based on what is given in the question, so they want us to represent it in this format. So if we do this, then the value of all these coefficients is an plus 1 is equal to 1, an as minus 1, and b as 0. So if you put those values in there, so you get the correct answers. Now, if we go to option two, that is the ghost point approach. So for that, it is mentioned that suppose this is my nth point, this is my n plus one point, and the question asks us to write the central difference, like equation for this using the central difference formula at node n plus one. So in the central difference formula, we know that we need three nodes. One which is before this, one is the node itself, and one after this. So that means we will have another node n plus two node and n plus two node. Now if we write the formula for this, so the equation is t quantity t x square is equal to alpha t minus t a. So if I write this, then it will become t n plus 2 minus 2 tn plus tn, uh, sorry, 2 tn plus 1 minus plus tn divided by, I think it is 2h square. Is it 2h square or h square?
H square, sir.
H square, right? Yeah. And then this becomes alpha tn plus 1 minus t alpha. Fine. Now the issue is that we don't know this t at tn plus 1 node. So let me just rearrange this. So we get tn plus 2 minus 2 tn plus 1 plus tn is equal to alpha h square tn plus 1 minus h alpha ta. So we get tn plus 2 minus 2 plus alpha h square tn plus 1 plus tn is equal to minus h square alpha ta. Now we take this as equation 1. So the other equation that the equation gives us is that the Newman boundary condition, right? So we just write, uh, yeah, so they have written to eliminate the ghost point, we write the Newman boundary condition using central difference formula at node n plus 1. This will result in another equation involving tn plus 2, and we can eliminate. So I write that, then we will get uh, tn plus 2 minus 2 tn plus 1. Sorry, we need to write the central difference formula tn minus 2 minus tn divided by 2h is equal to 0. Fine. So from this we get tn plus 2 is equal to tn. And now we just need to, like, this is our equation 2. So we have two equation. We got this term, right? Tn plus 1 is tn plus 2 is equal to tn. Just need to put this into this equation. Then we will get minus 2 plus alpha h square tn plus 1 plus tn. And then we have another tn plus 2. We replace that with tn. So we get 2tn minus h square alpha tn. Fine. Yeah, so they want us to represent to this to be represented as a n t n plus n plus 1 t n plus 1 is equal to minus 1. Okay. So it's given that ta is 25, alpha is 4, and h is 0.1. So h is 0.1. That means this becomes 0.01. Alpha is 4, and ta is 25. So this becomes 100, and this is 0.1. So this all becomes 1. And there is a minus sign. So this term automatically goes to minus 1. Now Tn, so the coefficient of Tn is 2. So An becomes 2 and Tn plus 1. So coefficient is minus 2 plus alpha h squared. So this becomes 2 plus alpha is 4. Yeah. 4 into 0 0.01 to 0 0.04. This becomes minus 2.04. Mm, yeah, I will share this and we'll yeah, so for the first part, the answers were minus 1, 1, and 0. And for this one, the value of an we got is 2, and the value of n minus 1 we got is minus 2.4. I think this should be correct. Yeah, yeah. Is this clear, Bhavesh?
Yes, sir. Please show me that notepad one time, sir.
Hello. Uh, any more Uh, just a minute. I think your voice is not coming. Can you repeat, Bhavesh, what you were saying?
Hello, sir. Am I audible?
Yeah, yeah. Now you're audible. Yeah, Bhavesh, you're audible.
Yes, sir.
Yeah. So is
Sir,
this clear? The both the two questions.
yes, sir. It is clear, but please show me the notepad, the calculator that you have done in notepad calculation.
Yeah. Okay. I will. Yeah, I will share that. Yeah. So what we just did is that we wrote
No.
the first. This one is the FDM equation at node n
Okay.
plus one. Fine. So we simplify this. We get this equation.
Okay.
Then the question gives us that we have a Newman boundary condition at T1. Okay. So we just write
Okay.
that boundary condition using central difference formula for node n plus 1. So this is the equation for that at node n plus 1.
Okay.
So from this we get Tn plus 2 is equal to Tn, and we put that back in this equation and we get equation in this term, and then we just simplify this to get the
Now it is
fine.
clear.
So do you have any more doubts?
No, sir. Yeah.
Fine. So I have few more questions prepared. Um, yeah. So Let us look at this Euler-Bernoulli problem. Even though it looks like a nonlinear problem, it's a linear problem because okay, let me go back to my tablet and I will simplify this. And then we will look at this using FDM approach only. So the problem is d squared y by dx square is minus t upon ei y is equal to wx l minus x to ei. Yeah. So we just need to write this using central. We just need to expand this, and rest everything is simple. So yeah, this becomes there is no term of y on this side, so we will just leave this as it is. We will just try to solve this part. Okay. Uh, this just changes the bi term. No other change happens because of this. So this becomes yi plus 1 minus 2 yi plus yi minus 1 upon h square minus t upon ei yi is equal to this. We just leave as it is. But still, like this x, it is a part of the ith node only, right? So basically what is happening is we have a beam like this, and the beam has a constant distributed load W applied on it. Okay. So this xi is basically the node location. So this is like x0, x1, x2, like this, x and plus 1. And yi is how much is the displacement this beam has. So suppose the beam displaces like this. So this is basically my y1, this is my y2, this is my y3, and likewise. So we have been given that the displacement at first node y0 is equal to 0, and displacement at last node yl is equal to 0. Okay. So this xi is basically the position of node, the distance of the node from 0th position, and l minus xi divided by 2 ei. Now we can just take that, multiply all of this with hi, and we get minus 2 plus th square upon ei yi plus yi minus 1 is equal to w h square xi l minus xi. Yeah, so this basically becomes our equation. Now, see, this is a linear equation in all the displacements of node. So we don't have any term with any dependent term with any of the coefficients, right? The problem, the first assignment problem, non-grid assignment problem, it's a nonlinear problem because we have like the yi is dependent on yi itself, and then yi minus 1 was dependent on the coefficient of yi minus 1 was dependent on yi. So that problem has a nonlinearity in it. This is a simple linear problem. We can convert this into a matrix form, sort of ax plus ax is equal to b form, and then okay, let me write this as, was confusing. Ay is equal to b, and then b becomes a inverse b. Y becomes a inverse b. Uh, so I will code this up. Uh, this we can try to solve again. Come back to this. Yeah. So let us first write all the parameters. W is equal to 5400. L is equal to 75. E is equal to 30. 10 to the power 6. Simply write 36. And I is equal to 120. Yeah. So the equation that we get is yi plus 1 minus 2, 2 plus th square divided by ei uh, yi plus yi plus 1 is equal to y not, sorry, I minus 1 is equal to, we get simple w h square x l minus x and divided by 2ai. Also, we know that for the first condition, for the first, okay, first we need to take division. So let us take 10 divisions, and L is given to us as 75, right? Let us take more than 75 divisions at least. Let us take 150 divisions. Uh, then H becomes so H becomes L divided by 1. Then our x values are, we need it. We need it. Just write this as x. So that becomes 0 to h to l. And the size of A matrix would be n plus 1 times n plus 1. B matrix would be n plus 1 times 1, right? Yeah, we know the display boundary conditions at both the ends. So we can simply write the first term of A matrix as 1, and for the B, it should be 0. Similarly, for the end one, we get and for B, yeah, for B also it becomes 0. We can see this from this equation itself. We get 0. This term would become 0. The last term would be also be 0 only. Fine. Because both are display boundary conditions. So this is the first term, and this is the n plus 1th term. Right boundary. Now we need to fill in the matrix values for the other terms. So I minus 1, that should be plus 1. This is this term, so that is minus 2 multiplied 2 plus t multiplied by h square, and then divided by p multiplied by next term is I plus 1th term. That should be minus plus 1. Next we have dith terms. Okay, so that is just this value over here. So I can just copy this, paste this, turn to multiply signs. Multiply over here, and multiplication over here. Yeah, this should be correct. So our y values would come a backslash b. So we will plot x comma y. Yeah, this should be correct. Okay, Euler Bernoulli beam. So we should get like we have a fixed boundary condition over here, fixed boundary condition over here. So we should get something like this, right? Let us see what we are getting. Error in this. Okay. Yeah. So this is like xi only, right? We have this x is the distance of that node, a specific node. So this should also be xi. Now this should be fine. Yeah. So we get something similar to that only. At node 0, we have a 0. And at 75th position is equal to 75, we also have a 0. Okay. So is this clear or any doubt in this?
It is clear, sir.
Fine. Okay. So let's look at another example. This one is related to. So this one is related to the mixed boundary condition. So at one end we have boundary condition is 3. So we have a Dirichlet boundary condition at, and on the other end we have a mixed boundary condition. So the first one is the boundary condition is a we know we have the derivative as well as position at that node. Or the boundary condition goes from 1 to 3. That means the domain of interest is from 1 to 3. Like it's not from 0 to 1. The domain of interest is from 1 to 3. Okay. So let us try to do this. So let us first create the functions. Yeah, first we will solve this using the boundary value problem, and then we will see how this changes the conditions in FDM. First we will use the BVP5C. For that we need two functions and one VB init condition, VB init function. So first I will create the boundary conditions. First I will create the functions. We don't have any other inputs, no parameters, so I will just write this. dy1 comma 1 becomes y2, and dy2 comma 1 that becomes 5 minus 6 into y1 minus 3 into y2. Yeah, this should be good enough. Next is the function for the boundary conditions. So residual boundary conditions x comma y. No, sorry, not x comma y. One at the right boundary and one at the left. One at the left boundary and one at the right boundary. This is residual at 1 comma 1. That should be the simple term. So YL1 minus 3. And on the other end, we have a mixed condition. So we need to use both YL1 1 and YR2, both the terms. So that should be YR. Mm, not 2. And the first one is 1 plus 2 multiplied by YR2 and then minus 5. Okay. Um, yeah. Is this clear? Uh, So we got the two functions for what we need for VPP. Now let us. So now we need the mesh, the 1D mesh. So let us create that. Yeah, len space. We are going from x is equal to 1 to x is equal to 3 in increments of let us say 30. Okay. And, mm, yeah. So next we need the BP init. So the initialization BBP. First input is the mesh, so that is our XVAL, and the next one is the initial condition. So I will give it 1 comma 1. Yeah, we have all the things. T5C. Let us solve using force this time. Yeah, so the input is first input is the function. Second is the boundary function. And the third one is the initial conditions. Right? So let us plot some C. What are we getting? I will plot both the things together. We have the function, we have the boundary conditions, we have the initialization, we have the mesh grid, and then this is the solution structure. Yeah. This should be correct. Let's see that. Yeah. Vectors must be of same length. What is inside solve? Okay. You can plot this x only then. So this x also goes from 1 to 3. So we can plot directly sol x. So sol 1. Okay. So now the first term is yeah. So the blue line is like it starts from 3. The red one is from minus 100. So blue one is the y values, and the red one is the displacement, the derivative dy by dx values. So we can see it starts from 3 and goes till something 2.3. Now let us look at the same problem using the FDM approach. Uh, Let us take N as 30, L is 2. Yeah, so we are going from 1 to 3, so L is 2. So H becomes L by N. We will create the X matrix. Even though we don't need it for the solution, we need it for plotting. So I will just create it. So it goes from 0 to L, not 0, sorry, 1 to H, goes to 3. So let us create the A matrix first. Like always, it will be a n plus 1, and B matrix would be fine. First, let us fill in the first one. So we know that this is given to us. So I will just fill this up. Yeah, like this we will get y as 3 always, y1 as 3 always. So this is left boundary. Let me try to write it over here. So we can write this as go back to the tablet. Stream, share without audio. Stream. So the problem is y double prime plus 3y prime plus 6y is equal to 5. Nilesh, do you have anything to ask?
Yes, sir. Am I audible?
Yeah, you are audible.
Uh, Sir, I have one question. When I'm solving assignment, it's for BVP 5C. It is error like
Can you just type in the chat? Uh,
okay.
you are audible, but there is a lot of background noise.
Okay, I will type message. No problem.
Yeah. Plus, is my screen visible to you guys, or is there some network issue?
No, sir, it is visible.
It's visible. Fine. So minus yi. minus plus 1 minus minus 1 2h 6 y 5. Yeah, so here I'm using the central difference approach. We can use either backward or forward difference. It will not change the answer by much. So let us use the forward. And so this comes minus 2. For VPP 5 set shows an error like a similar Jacobian encountered. What to do for this? I have changed initial inputs also. Similar Jacobian encountered. Hmm. Jacobian. Which question are you talking about, Nilesh? Jacobian basically that means you might need to check your equations what functions you are giving or definitions of the function, because probably it generates Jacobian for assignment 1 question. Okay. Let me see. Solve the above problem for two different values of k. K is equal to such which okay. Uh, yeah, Nilesh, I think you need to check the function, the main function that you are defining, where you are defining your equations. You need to check that there you are doing some error in that only, because rest boundary conditions those are not a problem, because these are simple boundary conditions. So boundary condition is not a problem. You are only making some error in the in writing of the functions itself. So just check that once. Otherwise, can I copy my code here? Uh, yeah, you can copy the code. I have to do this. Yeah, you copy the code. In the time, I will just do this. So I plus I minus 1. Square. So we get y plus 1 4 minus 2 plus 3h plus 6, no, sorry, not plus, minus 6 square yi should be 1 plus 3 and then plus yi minus 1 into 5 h square. So this is the equation which we will be iterating. Okay. And at the end, okay, param k l is equal to 1 and bvp net y initial z initial function bvp y y is equal to y1 and minus param k and minus y 1 minus y param k minus y. Yeah, Nilesh, check your function, VVP function only. Yeah, because dy by dx 1 comma 1, that should be z, not pi. You are doing the not discretization, you are doing the state space transformation wrong. So we are taking d. Yeah, so the equation is d square y by dz is equal to something. So dy by dz would be some variable. Suppose let us say in your case you have taken it as, I don't know what you have taken. So dy by dz we need to take as something like x. And then dx by dz would be everything. In your case, what you are doing dy by dz as y itself, and then you are again doing dy by dz as something. So it's basically you are using the same equation twice. Yeah, so I ran the program after correcting it. It is running fine. Also, one more thing, the functions should always be below wherever you are using. So in this case, like if you are using VVP5C at the end of the program, that is wrong. It should be before and all the functions should be after wherever you are calling them. So you need to also check that. Okay. Fine. Yeah. So this is the equation that we are getting. You guys can do it. So yeah, we need to check the last one. Okay? So the last boundary condition is y3 plus 2y prime t is equal to 5. So I will just write this as yi yn plus 1 plus 2 yn plus 1 minus yn divided by h is equal to 5. So yn plus 1 plus 2 by h 1 plus 2 upon h yn plus 1 minus yn upon h is equal to 5. So this is the equation for node n plus 1. Okay. Yeah. So so RA n plus 1 comma n plus 1 would be 1 plus 2 upon h. Bn plus 1 would be 5 and a n plus 1 times n, that would be minus 1 upon h. Yeah. So I will come back to MATLAB. To n a I comma I minus 1, that would be 1. A I comma I would be minus 2 plus 3 into h minus 6 into square. Yep. And then ai ai I plus sorry, yeah, I plus 1. This should be 1 plus 3 times h. Now the end boundary condition. So as I have mentioned, that should be n plus 1 plus 1 1 plus
Excuse
2
me,
upon yes,
code is not visible.
code is not visible. Okay.
The screen is not visible.
Yeah, is it visible now?
Yes, yes, it is visible.
Okay. Nilesh, do you have any more doubt? You can put your hand down. Yeah, so we were here. So an plus 1 would be 1 plus 2 upon h, and a n plus 1 comma n, that should be minus 1 by h, and b n plus 1, that would 5. Yeah. Then our solution is backslash b. This should be good enough. Okay, we need to have a b variable also here, so that should be or each of the calculations y plus 1 onto y plus 1 square y plus 1 minus I by h plus 6I is equal to 5. This is correct. Minus 2y plus y plus 1 3 h plus 6y h square is equal to 5h square. Collecting all the terms, I should be getting 1 plus 3h yi plus 1 minus 2 plus 3h minus 6h square yi plus 1 is equal to 5h square. So this should be correct. Let's see what we are getting. Matrix dimensions. These. Yeah, here the problem is. So it should be B1, not entire B. It's done. So this is going the other way around. Yes. Which is forward. Mm, 32 plus 1 down. Comma 1 B3 and rest is 2 to n. This is correct. This is 1 plus 3 is correct. 2 3h minus 6h square and minus 2. This is also correct. And these 5h square. That is also correct. The end condition is square. Yeah, now we are getting the right. So there was an error. It was not minus. It was not 1/h. It should be minus 2/h. I derived it correctly, but here I wrote it wrong. Yeah. So if I make that 1/h, then because it's Gauss, it's like backward elimination, right? So we are getting the last value in the end. So it propagates through to the entire all the y values. So we are getting something completely different, right? So I make this 2, and if I hold on, I plot this also on the same graph. So we have some, yeah, we have some deviation. That is probably because we are using forward difference. I think we should use the central difference formula. The forward difference sometimes the forward and backward difference is a little bit. They change the result a little bit because, like in this case, it's changing a lot. These two terms changes. If I would have used central difference formula, then instead of 1 over here, I would be getting some term over here and some term over here, and this would have been something different. So overall, the A matrix, it entirely changes. So that changes the problem structure. Usually, it is advised that we use the central difference formula for all the mid calculations, like for all this for loop calculations. And at the end, if some mixed boundary condition is given to us, then we should use the backward difference formula for the this end, and forward difference formula for the left boundary condition. Okay. So this is it. I have one more problem. So this is a nonlinear boundary value problem. Mm, just yeah. So this is also a nonlinear problem. We cannot do this using FDM. We have to either use Fsolve, or we have to use this VP solver. Okay. Uh, this you guys can do. I just want to look at this problem. How do we do this using FDM? It's interesting. So if we go back to that, we have this nonlinearity we want to solve. It's second order equation in CI. So if I initialize my F with something, if I initialize with some values of C, I need this to be 0. Okay, fine. So I make that I'm taking as input my C, and let me put DC values. So beta is given to me as 20, K 0.5, and I have taken C0 is given to me C. So now DC. DC1 is known. DCN plus 1 is known. Okay. So for each DCI, we have equations. K multiplied by. So we want this and that entire term to be zero, right? So let me just write this 2 times I square minus 2 times K right plus beta multiplied by H square square plus I plus 1 minus not minus. We have one term with Ci plus 1 and one term with Ci minus 1. So Ci minus 1. And this term is being multiplied by Ci. Yeah, this term is being multiplied with Ci. Then we have some other terms. Ci minus 1. Let me just take this to the next line. Ci plus 1 plus Ci minus 1. Yeah. And Ci and Cn plus 1, that should be C0 and Cn. And this is entire loop. Okay. So this is this, and DC is already 0. So the first DC1 and DCn plus 1 are already 0. We want all of these equations to be satisfied. We want to find the Ci values for all of these equations. So this is the equation that we get after the FDM approach. So we want this equation to be equal to 0. That means we want DCi to be equal to 0. Okay. Yeah. So now this function should return DC that it is returning. Okay. One more thing, let me type this as I so that it returns a column vector only. So if I save this, is it FDM non-line? Okay, function name. It is for this problem only, right? Wish, yeah. So I will just take the initial guess from here. 1, 2, 0. So I will just take 0.5 as the initial guess for this. Solve at the rate C FDM non-line, and we need the initial guesses. So H is 0. We have in total 11 nodes. We need 11 initial guesses. Let's see what we're getting. No solution found. It's not really converging to a proper solution. Okay. So if I give the initial condition as 1, this as 9, 0, then another 0. Still it's not converging. So this way it's not solving. C to C, C plus 1 minus 2 CI plus CI minus 1. D square C by dz square B C by K beta square by C. C minus 2 C beta CI CI K C minus 1. Let me simplify this. C K plus CI This is getting close to that, but it's not able to solve it properly. I look at the residual. Yeah, so F val, the second term is the residual. Yeah, so it is getting close to zero, but it's not entirely reaching zero. Is some better initial condition, but no, it's not converging. But I think you get the idea of what I'm trying to do.
Yes, sir. Yes, sir.
Bhavesh?
Yes, sir.
Yeah, I hope you're getting the idea what I'm trying to do. It's not converging, but the values are close to what we are expecting now. We are expecting, but still.
Yes, sir. I got it.
So what I'm just basically we know that it goes to zero. So uh, uh, yeah, we have I plus one. That is not. It should be. Yeah, I will try to do something else, and if I'm able to converge it, then end this meeting. Bhavesh,
Yes, sir.
do you have any more questions? We can end the meeting if you have no more doubts.
Yes, sir. Thank you, sir. Thank you, sir.
Okay, see you.